So let's say that I'm writing a C++ class, and or I'm writing in a C++ code base. I have need to encapsulate some stuff in a class, and I want to know what sort of boilerplate I add to this class. For example, it's going to need a constructor, copy constructor, destructor, all that sort of stuff. And in C++03, we all kind of learned that there's the rule of three, that if you have a copy constructor or a copy assignment operator or destructor, you probably want to have all three of those. C++11 made it more complicated by adding move constructor, move assignment operator. It starts to become cumbersome to implement all of these things, right? We need a rule of five, and then what about swap? And it becomes tempting to start implementing them in terms of each other. Is that a good idea? Is that a bad idea? So I decided that I ought to try to figure this out. This is what I came up with. So first of all, starting from first principles, there's a thing called the rule of zero. This was invented by Peter Summerlot, I think, said in 2013. The rule of zero is you shouldn't ever need to write anything. Right? Write your classes in a way that means that you don't need to declare or define a destructor, nor a copy move constructor, or a copy move assignment operator. You get the defaults. Right? The compiler will generate defaults for all of these. And the intent, obviously, I mean, the committee would not have given you defaults that did the wrong thing, right? You really want to have, you want to put yourself in a position where the defaults will do the right thing for you. And then you take the defaults, they do the right thing, everyone's happy, you don't even have to write any code. So that's what you want to get, rule of zero. The rest of this talk is mostly going to be about where the rule of zero falls down, because if it didn't fall down, you would just use it, and that would be the end of the talk, and it wouldn't be a very interesting talk. Okay, so how do we actually write our classes in this way so that we don't have to define any of these things and we can just take the defaults? C++11 makes it easier than C++03 because the standard library has so many more sort of utility classes in it. For example, unique footer, right, and shared footer, these things that manage memory for us. So if I'm writing, something that's going to manage a big buffer of characters, even in C++03, right, the answer is don't make that a char star, make that a std vector. Then your destructor does the right thing, and your copy assignment operator does the right thing, and you can just forget about it. So there's a refinement of the rule of zero, single responsibility principle. If I'm writing a class that deals exclusively with ownership, such as unique footer, shared footer, even like vector, right? A vector sort of owns the things that are in it. That should have all five of these special member functions here, the destructor, the move constructor, the copy constructor, and the assignment operators. If I'm writing a class that doesn't deal specifically with ownership, if it has another responsibility, then it shouldn't have any of these. And by the way, you can follow along if you have a laptop and you feel like spoiling yourself. There is a link there. You can go download the slides and follow along or skip ahead. So also in the links down here, we have links to the presentations and blog posts. Sorry. I will leave it there for a moment. So in the lower right corner, there are little clickable links to things that elaborate on the people whose work I am plagiarizing. All right, here we go. All right. Okay, this is a slide I've added since the Aston presentation due to relentless heckling from the audience. Howard Hinnant has a also very good presentation, which takes a very different approach than this presentation is going to take. His advice boils down to if you're implementing a class of any sort for any reason, give tender loving care to each of the 6 special member functions and really, really think about it and make sure it does exactly the right thing for your purpose. Maybe that means implement it yourself. maybe that means know what the compiler is doing and let it do its thing. But, you know, he would very strongly disagree with just about all the advice that I'm going to give you. Because I'm going to tell you, from my point of view, you know, I love rules that you can just follow and they just work.
Yeah.
So I'm going to give you things that you can do that if you do them, it will just work. And feel free to break them. But isn't it nice to have a default that will do the right thing? You might say, well, don't we have that? Isn't the compiler generated special member function, like the default implementation? I'm going to say equals default for everything. Isn't that the one that does the right thing? No, I'm going to show you why equals default is sometimes a bad thing. So what are the special member functions? All right. There are 6 of them. Default constructor, and of course the destructor, the copy constructor, copy assignment operator, move constructor, move assignment operator. By the way, how many people here have a good sense of what move semantics are in general? Okay, a fair number. If I say anything that you really don't understand, especially if you didn't raise your hand just now, let me know. I will try to clarify. And feel free to interrupt with questions by raising your hand at any point, because this is pretty informal. Whatever. So things that are not special member functions. Other constructors. The default constructor is special. It will get generated for you. Other constructors are not, and for the most part, don't interfere with stuff, except for constructors, which actually do interfere with stuff. If you define a constructor that takes anything, that will sort of turn off the default constructor. But, other assignment operators, same deal. Swap. Swap is becoming more important these days. Like Walter Brown, at least who's on the committee, thinks that swap is so important it deserves its own operator. He's been trying to get : equals : the swaperator, trying to get the swaperator into the standard. And, I don't think he's succeeding, but you know, it is. There is a vocal contingent that says swap is the really fundamental thing, and you'll see why in a moment. And something else that's not a special member function is comparisons, right? You might say, shouldn't they be able to compare for equality, you know, at least? But you know, you don't get those by default. Right? The compiler will not generate those for you. And the reason, by the way, historically, like why do we get certain things? Like why do we get a default constructor and we don't get like default like assignment, or we do get default assignment. Why don't we get default comparison for equality, for example? Because it seems like that should just be compare all the members for equality, right? Is because that's what C gave us, right? If I have a C struct, and I want to construct one of those on the stack, I can do that. If I didn't have a default constructor, I wouldn't be able to do that in C++. So basically, what you get for free is exactly the things that you need to implement C. Right? I can assign structs one to another, so I need an assignment operator to be generated by default. But in C, I can't compare structs, so I don't. So C++ didn't bother to generate comparison operators, but that might also change. So yeah, we'll talk about these, but not quite yet. Right? Okay. Sample code for testing. Here I put up. This is in Wandbox at that tiny CC link. This is just something where if I say something that you don't believe and you want to go test it for yourself, here's a base class that you can inherit from that will instrument the various methods and let you know what's getting called when. I will not usually refer to this again. I think there's like 2 places where I refer to this. We'll just move along. All right, default constructor. First special member function. What are some things that can go wrong with the default constructor? Right? The theme of this talk is pitfalls, places where you just do what comes naturally, something's going to go wrong. What could possibly go wrong with defaulting your default constructor? Here's a case. This is basically actual code from a former employer's code base, where we were trying to implement a sort of a type system inside C++. We're trying to emulate the types of another language in C++ by making up, a string type and an int type and so on. And we would have a unit test that would test that I can make an int and then, it would implicitly convert to a string if I needed that to happen, and so on. We have this code. If I compile this code, what happens? The answer is it works perfectly. There's no problem. We are able to construct things. We are able to assign them. Nothing has been turned off. It just all works. But we take this same code and we change that std string template parameter to an int. And suddenly, when we invoke the compiler on this one, we get a whole spew of error messages. And the reason that we got this whole spew of error messages is in this test, we have, let's see, t is int. So we have right here, cursor, yeah, okay. We have a member of type int, and it didn't get an initializer, right? Because we defaulted the constructor. So that means int got default initialized, so it's initialized to basically garbage. And that means that due to a weird little paragraph in the standard, we go to make a const one of these guys, and the compiler complains to us that we have an uninitialized const variable here. If a program calls for the default initialization of an object of a const qualified type T, T shall be a class type with a user-provided default constructor. In other words, I can't say const double D semicolon. That is not allowed. But similarly, I can't say const foo f semicolon if f has a member of type double, unless f has a user-provided default constructor. Now all I need to do to make this example compile is take this equals default and change it into a pair of empty braces. That has exactly the same semantics, except that now the default constructor has become user-provided, and therefore the compiler is perfectly happy. It has exactly the same semantics. There's still no initializer for that member, but it works. So that's an example of something that can go wrong if you just take the default. And you might say, why would I ever write this code? This seems like dumb code. But the answer in our case was we just had a Python script that generated our unit tests, and it wanted a const t, and it decided, well, I'll declare a const t. Because I just want to check that this all compiles, and the answer is, well, it didn't compile. So what about the destructor? So if I give my class a destructor, I have now completely broken the rule of zero, right? I have a 1, so that's more than 0. I've broken the rule of 0. And now as soon as I have that, it's going to turn off pretty much all the defaults that I would otherwise be getting implicitly. You don't get your implicitly defined move constructor or move assignment operator. You do get copy assignment and copy construction. But as of C++ 14, that's deprecated and probably going to go away, I would say, 17. The idea being that if I'm doing something in my destructor, I'm basically saying I care about when this object is destroyed. I care about when objects of this type are destroyed. That means I almost certainly also care about when they're created, right? If I'm like decrementing reference count in the destructor, I probably want to increment the same reference count in the copy constructor, for example. And I probably also want to do something special with the move assignment and so on. So that's the rationale behind why destructors are magic. So we have here another puzzle. What does this print? Here I have a construct widget, and it's just got some members in there, and it's got a destructor that does nothing, right? A pair of empty braces. Maybe there's an assert in there that gets compiled away. Maybe it's just a pair of empty braces. In main, I am trying to move assign W2 into W. Spoiler. It does a copy assignment. So even though I said move, what I get is a copy. And the reason that I get a copy is because having defined my own destructor, I have turned off the move assignment operator. So the move assignment operator doesn't exist anymore. But the copy assignment operator does exist. So this picks up the copy assignment operator and uses it. So the moral of this story is it's very, very easy to create a copy-only class without realizing it. Right? 'Cause even a pair of empty braces here is doing something to my class that if I just said equals default would not have done. Oh yes, another bonus slide here. This is from the same talk by Howard Hinnon where he says give tender loving care to all of the members. This is what the matrix looks like right now for if I as the user declare one of these things, what happens to all the other special members? The boxes in red that say defaulted are the ones that are deprecated. Notice that some of the others, I think some of them say deleted. Yes, some boxes say deleted, some say not declared. The difference there is very subtle, and I'm not really going to talk about it at all. But basically, deleted means does participate in overload resolution, but if it's ever selected, then you have an error. Whereas not declared means it's not there at all. Yeah. Anyway, this is like if you want to go look at these slides, you have a reference in here. I'm not really going to talk about that. All right. Destructor. Going back to the destructor. You might think, if you thought about this before, you might say, oh, he's going to talk about the destructor and what you need to do with the destructor. I've heard that you should make your destructor virtual. When should I make my destructor virtual? Herbslutter says, if you're intending to use your class as a base class, and if you expect callers to actually take a pointer to your class and destroy it and get the polymorphic behavior, then you should make your destructor virtual and you should make it public. Otherwise, make it non-virtual and make it protected so that people can't call it by accident. Good advice. But I am not going to talk about this much because mostly what I'm talking about here when I talk about the rule of 0 and the rule of 5 and so on is talking about value semantics, how to get your objects to play well with move semantics and passing them around, returning them from functions, things like that, which you really shouldn't be doing if you're doing polymorphism, if you're doing passing around pointers and calling virtual methods. Polymorphism, value semantics do not play well together. Here's an example of what happens when you mix the two. So here I have a class, dog, right? Base class. I have two derived classes. I have fox terrier and I have direwolf. I create a fox terrier and a direwolf. I send them to the dog park. Now, as far as the dog park is concerned, these are both just dogs, right? I have a reference to dog 1, reference to dog 2. I should be able, they're both dogs. I should be able to do whatever I want with them, right? I should be able to move assign one to the other or swap them or, copy construct one of them and it should all work. Turns out that does not work very well when they are different sizes. This will not at all do what you want. There will be some splicing involved because we're going to be move constructing a plain old dog from a fox terrier, and then we're going to be trying to move that dog into a dire wolf, and that's going to, I don't even know if that's going to compile, depending. It's terrible. Terrible, terrible idea. Yes, so what this means is that for the rest of this talk, we don't even have to worry about virtual. Oh, right, also, yes, if you have virtual-based classes, it gets even worse, because then you don't even know what your assignment operator is doing anymore. Okay, so we're not going to talk about inheritance. Copies. So I took AP Comp Sci back in like 2001, and I wrote a lot of code in that class that looked like this, right? Where you want to prove that you know what the copy constructor does and what the copy assignment operator does. And so you go and you write it out explicitly. Here's what it does, right? If you do this on the APCS test, and then you look at it 2 years later and say, what was I thinking? Why did I write these? These would have been implicitly generated for me. So don't write this. Modern equivalent is we can just say equals default for all of these. Great, that's perfect. However, if I'm just defaulting these, I have mentioned them. And so we will still get down here copy assignment. I said I have copy members. I didn't say anything about the move members, so they got implicitly not declared. And so I, again, accidentally have made my class copy only. Even though I updated it to be C++11 compliant and I added the equals default instead of the empty braces or whatever I had up here, I still, again, accidentally made my class copy only. I pessimized my class unnecessarily. Here it would have been perfect to just use the rule of 0. Right, so certainly do not prove that you know how to implement the defaults by implementing them yourself. That's just wasted typing. Even explicitly equals defaulting these guys is going to get rid of your move operations. Also, if you have copy operations and you explicitly equals delete them, you say this class cannot be copied. Since you mentioned them, that will also trash your implicitly defined move ops, and you won't have a move. You won't have a move only class. You'll have a not anything class, not move. So don't do that. So there are a lot of ways to make a class copy only. Beware of them. All right. So turning to the theme, the implicit definitions are often correct. The implicitly defined defaulted copy constructor will copy construct all the members one by one. The defaulted copy assignment operator will copy assign all the members one by one. What are some ways that this could go wrong? We saw a way in which the default constructor's default definition can go wrong. How about the copy members? How can they go wrong? Semantics. What's that? A member that's initialized on the heap. Why?
If you knew anything.
If you knew anything, then how would that go wrong?
Oh, well, it just copies.
Oh, okay. Yeah. So yeah, if I have like raw pointers and then if I just copy construct one of these, I'll copy the pointer, but I won't copy the stuff it points to yet. Yes. We could get around that, if it's something like a buffer of characters, I could put it in a std vector, and then the std vector would the right thing. Which, yes, gets sort of back to the rule of 0. Like, if at all humanly possible, you want to design your classes so that you do wrap these things up in vectors or unique footers or something like that. But actually, speaking of heap allocation, that is sort of related to where I was going with this, which is, let's suppose that copying one of these resources does, let's say, allocate some memory. And then I do another copy assign that allocates some more memory for the second member. And then I copy assign the third member, and that also allocates memory. So any one of these allocations could throw, right? Let's say that I have this name here that has first, middle, and last represented as strings, and strings copy assignment operator, since it needs to allocate memory, it might actually throw. So here in my main, I have the loop that just, while we haven't run out of memory, lets new of a new name, default initialized to all the strings will be empty string, and then set it equal to Jerome K. Jerome. At some point, I'm going to throw, and when that happens, I'm going to assert that, well, either the first and last name are going to be default initialized to empty string, or I will have assigned Jerome K. Jerome to it, so they should both be Jerome, so again, they should be equal. And I'm going to find that this assert actually fails because I've got a copy assignment operator here that doesn't respect the strong exception guarantee, right? It just copies the first one over, makes it equal to Jerome. Second one, do I have an example here? Yeah. So here's what gets implicitly generated for me, right? I try to copy over the K, that throws, and I never get to the part that copies over the last name. So I end up with a partial result, part new value, part old value. So we don't have the strong exception guarantee, which, if you're not familiar with that, the strong exception guarantee is if we throw, then we'll be in a consistent state. We'll have done nothing, basically. The basic exception guarantee is that we don't leak resources, and that's still true here. We're still in a reasonable state, but, well, we're in a reasonable state, but it's not a state that is consistent. We're in this weird middle state that we can't really get out of because we don't have the old data anymore because we overwrote some of it, but we also don't have the new data because we didn't finish writing it. So we're just in a bad state. So here's how we fix that. A very well-known copy and swap, right? If we're going to put a value, new value into our object, we need to do it in a way that doesn't throw. So we're going to construct the new value somewhere off to the side, make sure it's completely constructed. If it throws, no problem, because we haven't touched the old value, we still have it. Then we're going to swap the two of them, which we can do without throwing at all, right? Because they're both there. We need to swap some internal pointers. That can't throw, so then we have the new value. Then we can destroy the old value now that it's off to the side. So this is great, this works. Questions about copy and swap, by the way? I don't know why I think there would be questions, but.
So you're recommending to use this technique? You don't want to have that intermediate state? With the exception?
Yes, I would say if you cannot afford to give tender loving care to all of your special members, then yes, this is an excellent foolproof way of getting something that has a strong exception guarantee.
Copy and swap medium would not work if you don't get your copy constructor right.
Yes, you still have to write your copy constructor. However, the default copy constructor, which looks basically like that one, will actually basically do the right thing. Like I could not think of a way that would go wrong. So equal defaulting that one, or at least giving that one tender loving care, but then you don't have to care about any of the others. You just cut and paste the copy and swap idiom, and it should work. It may be slightly less efficient than writing your own by hand, right? For example, in this case, if we're thinking about how do I implement the copy assignment operator for vector, maybe it would be more efficient to, I already have this memory over here owned by this vector. I have the memory over here. Maybe I should just copy each element one at a time and be able to reuse this memory rather than allocating a whole new buffer and copying everything in that and then swapping them and then deallocating a buffer. Maybe I can just copy right again. But of course, the point is that I can't do that if copying an element might throw. So now there are plenty of code bases where we just don't care about exceptions, right? If you don't care about exceptions, then this isn't really buying you anything, other than being a nice idiom where you can just sort of remember, like, this is the code I write for this. Yeah.
What are the assumptions behind the swap? The fact that swap assuming you know exact. First restraints, but if you're writing your own, you have to actually make certain rules.
Yes, swap in this instance has to be noexcept, or at least has to not throw an exception. Yeah, come to think of it, it might be good to mark it noexcept, although I have not done that in any of the following slides. But in pretty much every case, you can write a swap that won't throw, right? I mean, you'll have two objects, they will have certain guts, and what you need to do is swap the guts. All of the standard library containers and so on have swap either member functions or free functions that are guaranteed to do the right thing. So
I think it's requirement for most of the standard library that uses swap and requires that the swap be so.
Yep. Although we're gonna really rip into swap in a moment too. So all right, so the move operations. Let's see, is this a move operation? It is, yes. The move constructor, again, the default will pretty much do what you want. The move assignment operator. This might also be controversial, but you can implement move as swap, because what does move do, right? It makes the left-hand side equal to the old value of the right-hand side and leaves the right-hand side in unspecified state, unspecified but valid. The way we're going to do this is we're going to steal the guts of the right-hand side, and we're going to put them in the place of the guts of the left-hand side. The problem is we have now the left-hand side's guts, and we don't know what to do with them. We have to either put them somewhere or destroy them. We could destroy them. That's a little expensive, and we have to, how do we do that? We'd have to write a cleanup function that was called from both here and the destructor, I guess. It's much easier to just, well, we have an empty object over here. We've just taken the guts out of that one. We have some guts we don't know what to do with. Let's just put them over there. And in most cases, the right-hand side is an R value that's going to get destroyed anyway. In some cases, it's not. And in those cases, if we're implementing something like a smart pointer, like we're implementing unique footer, then we really don't want to use this idiom, because nobody would really expect that move assigning into a pointer that controlled a certain resource. You expect that if you move something on top of it, it will deallocate the old thing, right? Not just move it over somewhere else and keep it alive. So there are cases where this is not necessarily the correct thing from the user's point of view, but for most cases, we can get away with this. Okay, so what could go wrong with this code? Here's the most entertaining way in which this can go wrong. This is the same code from earlier, but I've added at the top using std swap. Because we didn't actually say how we were going to implement swap, right? We said that we could theoretically implement it in a way that didn't throw. But just looking around at, well, where can we get swap from? Well, when I try to compile this code, the compiler says, no, I don't find a swap. Did you mean std swap? Well, okay, sure, I mean std swap. Let me just put that there. And then I try to compile this, and what happens? It compiles perfectly. And then I try to run it, and I get a segfault on this line, which makes no sense, right? Calling itself recursively, yeah, because my move assignment is calling std swap. And how is std swap implemented? Well, I don't know. Let's read the standard. Standard says swap. Noexcept blah, 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 requires blah, 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 effects. Exchanges values stored in two locations. Now, it doesn't really say which two locations, or how the values in them are going to be exchanged, or really what a value is. But this is what the standard has to say about it. So if we want to know what it actually does, we go and we look at any old implementation, and we find out that this is how it's implemented. It's implemented as a move construction, followed by a move assignment, followed by another move assignment, followed by a destruction of the thing we constructed. So yeah, so std swap implemented in terms of move. So therefore, if we're going to implement our move in terms of swap, we'd better write our own swap. Right, so yes, move implemented swap, swap implemented move. Don't use std swap in your global namespace anyway. Where are we going with this? Where we are going with this is, we'll come back to swap in a moment. I want to digress and mention one really kind of nifty possibility that I've read about, never actually tried to use, but again, there's a link in the lower right corner if you want to read more about this. But it's possible to make a copy assignment operator that doesn't take a reference at all, just takes the right-hand side by value, which means that anytime you call the assignment operator, you're actually making a copy of the right-hand side already. As the caller has to make that copy, and then all you need to do is swap with that copy, and then the caller destroys it, and works great. It looks like this might involve more constructions and destructions than doing it with references. But in fact, at least in that third case there, where I'm copy assigning from an R value, since I'm moving the result of calling R directly into temp, we can actually move allied, do move elision there. And so I don't actually have any temps involved at all. So yeah, yes, this trick is valid. I'm not sold on it yet. It's interesting. If anyone is actually using this in production, I would love to hear about it. Find out if it works and if it's causing more confusion than it's solving. But anyway, yeah, you can totally do this and get rid of your other two assignment operators if you want. Okay, so what do we do about swap? Coming back to swap. How do we implement swap? There's this thing called std swap. It's a template. So we could specialize the template. There's also a whole bunch of free functions in the std namespace named swap, and there's a swap for strings, there's a swap for vectors. So I guess we could overload it by providing our own swap function in the std namespace. We could provide a free function swap in our own namespace instead of namespace std. And we could locate that via argument-dependent lookup. Or we could provide a member function swap, like vector has you can, if I have a vector v, I can say v.swap v2. So basically, what constructs do our users expect are going to work? Then we need to make those work. Okay, let's talk about the first two of these options, specializing std swap and overloading std swap. Specializing std swap is actually allowed. The standard says a program may add a template specialization for any standard library template to namespace std if the declaration depends on user-defined type and the specialization meets the standard library requirements and is not explicitly prohibited. All of that verbiage basically means, yes, you can specialize std swap. I think that's pretty much the only use for that. That and numeric limits. You might want to specialize numeric limits for your big num type or something. So you can specialize it, but you're not allowed to add any declaration or definition to namespace std if it's not a template specialization. So overloading std swap is right out. Do not do that. Specialization is allowed, but it's a bad idea. And the reason it's a bad idea is because it doesn't work for everything you might ever want to use it for. It works fine for class widget because we can specialize swap for widgets. It does not work for gadgets because we cannot specialize swap we cannot partially specialize swap. We can't say, here's a specialization that works only for gadget of t, but I'm not going to tell you what t is, right? We can make a specialization for gadget of int and a specialization for gadget of double, but we can't make a full specialization for all gadgets, but only gadgets. So we can't use it for gadgets, so we shouldn't use it for widgets. We should figure out some way that is actually going to work in every case and do what we want, right? So the right answer is, as you probably already guessed, this is probably not super surprising. Provide an argument-dependent lookup swap, which means provide a free function swap in your own namespace. And it can be implemented in a pretty obvious way. Now we can provide this function swap, but it's not going to be a member function. So we're going to have to make it a friend. This post, by the way, if you're a C++ geek, check out that blog post. It's crazy good, yeah. Which points out that we might be tempted to take this function swap and inline it into the class, like so. This is actually legal syntax. You can just define friend functions right there inline in the class, and it's tempting to do so because it kind of makes sense. This is a member function, but it's very closely tied to the class, and it's fairly short, and it's nice to just keep everything in one place, right? So you can do this, but if you do this inside the class, you're actually putting that free function into a sort of hidden namespace that's not the namespace outside the class. It's not the global namespace, but it's also not the namespace. You can't get at it by saying name : swap either. It's this weird hidden namespace that's only accessible to argument-dependent lookup, which means I can say, swap widget 1 with widget 2, name 1 with name 2, and it will find it. But if I try to access just that name directly, as in this last line here, this, which would work with the previous slide, has now stopped working. When I gave this talk on Friday, I kind of realized this in the middle and decided that maybe this wasn't the right way to go after all. Maybe the way that we want to go is to just do what string and vector and so on do, which is provide a member function swap, and then we can provide a free function swap that does the same thing. It no longer needs to be a friend because it's not accessing anything that's not part of the public interface, just delegating to the member function. And so we get this, which looks very conventional and actually very verbose, but ends up doing the right thing in all our cases, except unqualified use of std swap. Right, the second line here, where I try to std swap widget 1 with widget 2, that's of course going to use std swap, which is implemented in terms of 3 moves, and it's not going to be very efficient, especially since my move is implemented as swap. So really, what's doing when it does those 3 moves is swaps. So I've implemented swap as 3 swaps. But anyone who makes qualified calls to swap in a template is doing it wrong. Right? They did swap of A and B. Congratulations, you probably found a bug. Everyone should be using unqualified calls to swap. Using std swap semicolon, swap A with B. All right, so let's get to what I consider the most interesting part of this talk, which may not be saying much. Here we have some code. This is code sort of reduced from a GCC bug report. We have a class person that has a member of type vector, vector of string. It's all standard types. And we have a non-uniform shuffle function, which just repeatedly picks elements from a vector and swaps them with each other. And we're going to try to shuffle a vector of people. What could possibly go wrong with this? I'm just going to go ahead. Oh, yes.
Swapping with yourself.
Swapping with yourself. True, but that should be a no-op, right? I mean, just swapping a thing with itself. Yes, this is where we're going with this, though. Because we're swapping a random element with another random element. They might be the same element. When that happens, we end up swapping an element with itself. When that happens, at least on GCC in debug mode, you get an assert fail at runtime. Says error attempt to self-move assign, and it just crashes your program. Doesn't even throw an exception, just like boom, dead. So this was pretty terrible. Someone filed a bug report about this, especially since this was actually happening at the time in the GNU standard library's implementation of random shuffle, like the actual random shuffle algorithm. If you tried to do that with vectors, it would just crash. They did fix this. The bug report has been resolved. They fixed this by adding a test in random shuffle so that it would no longer attempt to swap items with themselves. However, if you write your own little test program, you can very easily did the same thing. Right. The reason this happens is because did swap is implemented in terms of move, and if we swap something with itself, we've got this line that tries to move something into itself. And this is the thing that triggered the assertion, right? The attempt to move itself. Standard types, container types, and class types defined in the standard library do not support self-move because, as the standard says, if a function argument binds to an R-value reference parameter, the implementation may assume this parameter is a unique reference to that argument. In other words, anytime I take an R-value reference, I can just assume that it's not the same as any other, that doesn't alias anything. Particularly, it doesn't alias this. So the implementation is free to optimize away aliasing checks which might be needed if the argument was null value. The move assignment operator is a function. It's a member function defined in the standard library. It takes an R-value reference parameter. It's going to then assume that that R-value reference parameter doesn't alias anything else, in particular, it doesn't alias this. That assumption is false. Therefore, anything can happen. Right? In other words, this is undefined behavior. Doesn't actually it could just use the words undefined behavior. It doesn't really need to talk about optimizing away aliasing checks, but read between the lines, this is undefined behavior. There are a few exceptions, or possible exceptions to the rule, because you'll notice that this the preamble to this bullet point says each of the following applies unless explicitly stated otherwise. And there are some places in the standard where it looks like they're explicitly stating otherwise, or at least they're stating otherwise. Maybe explicitly, maybe not. All the smart pointers give very specific sequences of, when you transfer ownership of a unique putter, that's the same as calling reset of release, which would do the right thing. Except that says as if, and it doesn't explicitly refer back to the other place that said it was undefined behavior. So I don't know if I would count on that. And in fact, did string, basic string, its move constructor said very explicitly in the standard, if this and stir the right-hand side are the same object, then the member has no effect. Perfect, excellent. This is exactly what I would like to be always the case, is that, if I move something into itself, there's no effect. This was brought to the attention of the committee actually super long ago, like 2003 or something. Sat in the defect report for a long time, and just a couple of weeks ago in Lenexa, Kansas, they had a committee meeting and they fixed this. They struck that paragraph entirely and said, never mind, we were wrong. This member does have an effect, it's undefined behavior. So that should have made everyone happy. And since they decided there that the undefined behavior of self-move was so important as to override this very explicit sort of statement, I would say probably you shouldn't rely on it working in any case. You just assume self-move is strictly a bad thing, off limits. Right. Default move assignment operators cannot be trusted, which means if you have a member a data member of a standard library type like vector or string, your default move assignment operator is not going to work for self-move, which means if you have a code base that might rely on self-move working at any point and not like crashing or doing the wrong thing, getting rid of your data, then you should probably implement a move assignment operator yourself, called the rule of at least one. If you implement the move assignment operator yourself, then you have to implement the move constructor yourself. If you implement the move constructor yourself, you have to implement the copy operations yourself. So we're back to basically square one. We have to implement everything ourselves, or at least think about it. But then you just cut and paste that copy and swap stuff, and it works. You might say, okay, well, I don't have to worry about self-move, because I would never, explicitly move something into itself. I've audited my code, and I don't do that. And I don't use unqualified calls to std swap. I always say, ADL swap of X with something, and because I implement my own swap, it will just work. My own swap maybe checks for self-move even. Haha, my code is foolproof. I would argue that in general, you don't want to do that because all of us, if we're writing code for a large code base or for your company's code base, or you're distributing a library yourself, you don't know how people are going to use that 6 months from now, right? Someone could be building on top of your library. And if you leave this little trap in your cat class, right? Here I have a cat. Everything I do with my cat works great because I know what to avoid. And I can even assume that all my coworkers know, and they're never going to write a qualified std swap, and they're never going to write an explicit std move into self. But they might do this, right? Now, instead of a cat, my coworker has written bag of cats that has 2 cats in it. And he does an ADL swap of 2 bags of cats. But bag of cats implementer has omitted to actually write a custom swap function. So when we do an ADL swap, we don't find a custom swap implementation for bag of cats. What we find is std swap. And std swap is implemented in terms of move assignment of bag of cats. And move assignment for bag of cats gets the default implementation, which is implemented in terms of move assignment of the members. And move assignment of the members has been defaulted. And so it's going to try to move assign a vector into a vector into itself. And everything's going to blow up. So one of my theses here is that vector and string and so on that have this undefined behavior with self-move, that may be efficient, but it leaves a pitfall for anyone using those. And you can navigate the pitfall yourself, but I would argue that it is antisocial to leave that pitfall in your code for the next guy to also fall into. If you're going to the trouble of navigating around it, you should just make it work, and then there won't be a pitfall for the next guy implementing bag of cats. So we're getting near the end here, fortunately. What we've come up with here shouldn't be surprising at all, really. This should be pretty conventional. But notice all the little pitfalls that we've mentioned here, the defaulting of the default constructor, using the copy and swap idiom to get the strong exception guarantee, how to implement swap so that everything a user could possibly do would just work. Oh yes, yeah. Slide on const expert. People would ask like, oh, well, I'm implementing this widget, and I've heard about const expert. It seems great. I kind of want people to be able to use this class in a constant expression or something. Should I just make all my members const expert? Turns out, no. That you can't have const expert members unless you are what's called a literal type, which means, among other things, that you have to have a trivial destructor. And we saw from earlier that even just putting empty braces or assert true in your destructor will make it trivial. And then, as soon as someone does that, just tries to stick anything at all in your constructor, all of your context members will fail to compile, and we'll have to go manually backspace out all your context words. It just seems to me very fragile. So unless you're designing a type specifically to be a literal type, like you're designing integral constant or something that you expect people to really use as a metaprogramming tool, I would not bother at all with constexpr. And noexcept. We mentioned that possibly swaps should be noexcept, but it doesn't need to be. But the one place that noexcept really leaks into concerns about efficiency is if you make your own move constructor, and you make it like in this example. Here I'm doing the APCS thing of just writing out the default for no reason. But suppose there was something else that I were doing there that were more complicated. If I just write this, and then I make a vector of bad cats and push back 100 of them, at some point the vector is going to need to be resized. And when that happens, it's going to need to move all of the cats from the old vector into the new vector, because it's now reallocated that space and it needs to copy all of them, right? And it should just be able to move all of them. But the problem is, what if one of those moves throws? Then, in order to provide the strong exception guarantee, which vector actually does provide for resizing, we would have to still have the original cats still in the old vector so that we could return that. If we start moving them over here and one of those throws, what are we going to do? Move them back, but it could also throw. So what we do, if moving cannot throw, then we can just move them all. Moving can throw, then we have to copy them instead, so that we still have the originals, so that we can roll back. The way that vector ends up doing this is here's a ton of standard E's. And if you don't know about this already, you probably are not going to infer it from what the standard says. But reading between the lines, what it says is we need to provide the strong exception guarantee. Therefore, we're going to try to move construct these things. But if the move constructor is not explicitly marked noexcept, then we are going to copy them instead. So therefore, if you provide your own move constructor and you don't mark it noexcept, you are SMizing your code again. If you're going to store them in a vector. If you're not going to store them in a vector, it doesn't matter. Very special case. All right. That is officially the end. Thank you for bearing with me through this slog. And if anyone has any questions or would like to see 2 slides of bonus material, thank you very much. What's the bonus material? So we talked about swap and how to provide it using a member function, free function. I would argue that comparisons can be provided in the same way, and would like to see this incorporated into a future standard. Eric Nickler has a very interesting proposal out for what he calls customization points, where swap is like a customization point, where if you provide your own swap, the standard library will use that whenever it needs to swap things. It would be nice to see a 3-way comparison function also as a customization point. Implement a compare, for example, that does the spaceship operator, right? Gives you less than, equal, or greater in a single operation. And for some things like tuples, particularly tuples and vectors, that's very efficient, more efficient than doing a if less than one thing, else go back and compare them again to see if they're greater. You can do compare the same way. And then the other bonus material, pointer to implementation, a pimple, is an idiom that I think was more common like 10 years ago, but I don't know. Do people still use pimple? Has anyone here used it?
On occasion.
On occasion. That's basically where you want to hide the implementation of your object-oriented class. So you want to say, here's my public interface, but you don't even get to see my members or how big they are, because the only private member of my class is a pointer to the implementation. So I have a struct impl and a pointer to the implementation, and I hide the actual implementation of struct impl, such as how big it is and so on. I'm going to hide that off in my implementation file, my CPP file, and you're not going to get to look at it. C++11 gives us unique footer, and you might say, well, this is great. It was a pain to have to manage this pointer manually, right? Because I have to new it in the constructor, I have to remember to delete it in the destructor, I have to remember to move it around in the move constructor, and copy it in the copy constructor, and do all these things. So it's kind of tempting to say, okay, let me use unique footer. Let me use the library's unique footer. So at least I get a lot of this for free. I get the move constructor for free, right? Just does the right thing. So I try to implement it like this, and I get an oops on the line marked oops. It doesn't compile. And the reason that it doesn't compile is while I'm trying to construct a widget, and that works fine. But also, implicitly, when I construct it, at the end of the scope, I'm going to try to destruct it. When I try to go and destruct a widget, I'm going to get the default destructor, right? Because I didn't provide one, so I'm going to get the defaulted one. And what that's going to do is try to destroy the member. So it's going to try to destroy my pointer member, my unique footer member. And the destructor for unique footer is going to attempt to delete what it points to. And for that, it needs to know how to call impulse destructor. An impl is not defined in this file. So it says, I don't know how to destroy an impl. You didn't tell me. So we get an oops. So we try to fix that. We add tilde widget. Right? And we say, okay, well, instead of trying to do the default thing when you destroy a widget, I'm just going to provide with the destructor. Just call that. And you define your destructor over in the other file where you can see the definition of impl. All works fine. And your code compiles. There you get rid of the previous oops. Unfortunately, you get a new oops. Now when I try to return a widget from a function, I get an oops. And the reason that I get the oops here, I guess is, by the way, quite a puzzle. Move. Right, so return widget is going to try to use the move constructor if it can. But the move constructor is not declared because we've given ourselves a user-defined destructor. We gave ourselves a destructor that turned off the move operations. So we don't have move operations anymore. What do we have? Well, we have copy operations. Unfortunately, the copy operations have been defined as deleted because you can't copy a unique footer. Right? Unique footer is move only. Because it's unique. So what this line of code is doing, the nature of the oops is we would have looked for a move, but there's no move. So we go look for the copy, we find it, it's deleted, and we get a compiler error because we're trying to access a deleted copy constructor. Which might not even make sense if you're trying to read that error message and saying, what do you mean deleted copy constructor? A, I didn't delete the copy constructor, and B, this should be a move, shouldn't it? But no, we have written ourselves into a corner here. And then the way that we get around that is we provide our own move constructor, and then we can get around that. And then of course we have to provide our own move assignment operator, and so on. And we get back to the old 5 of, define everything. That's really the last slide. That's the end of the bonus material.
The previous bonus material.
Fun.
Trying to compare there's also a boost operators library that can basically give that you don't actually need to specify the minimum set of operators and provides the rest of them in in terms of the minimums that you provide?
I don't know about boost. I do know that there's an actual thing in the standard called std::relops, which has templated definitions of free functions, operator equal equal, operator greater than, operator less than, et cetera, that are then defined in terms of simpler operations like less than and equal equal. Two problems with that. One problem is that puts the burden on the caller, right? Any client code of mine has to now say using namespace did relops in the code that they want to use these operators with, right? So they have to say that everywhere they're going to use it.
I mean, the basic question which the boost one you derive from class.mySem, so it's implicitly included.
Okay. In that case, that is better than relops. Relops I consider completely useless. But the other thing that probably does not do is things like tuple and string comparison, right? Like std string, for example, has a compare method because what is it compared to with a strcomp, right? And what is the interface to strcomp? It gives you less than, equal, or greater, a single return. Because and the reason that they chose that, the reason Cardigan and Ritchie chose that interface for strcomp is because that's the most efficient, right? You're going to go along until you see a different character, and then you're going to know at that point less than, equal, or greater. If you just returned a bit that said, well, it's not less than, like, well, okay, well, is it greater than? And you have to go back and go through all the characters again. So for anything that has lexicographic ordering, like strings and tuples and vectors and so on, really you want to get all of the bits at once. You want to get, is it less than, or is it greater than, or is it neither? So
it's ideal for every circumstance, but
there are cases probably where you could do equality comparison more efficiently than all three comparisons. But wouldn't it be nice if we had just a like tuple comparison and so on?
Question on the non-group material. You tie back kind of your end to your beginning. Given the issues that you pointed out with swap, where do you stand on the rule of zero? No longer recommend that you write anything such that you don't need any, because if you use anything, you're going to have to provide your own swap.
I am of many minds about the rule of zero. I mean, honestly, my take on it is basically hope that you work in an environment that you don't care about the strong exception guarantee and you don't care about self-move, and then the rule of zero works great. But I am not sure whether those environments exist to the extent that I want them to. Like, you may think that you don't care about the strong exception guarantee, and then one day you find out you do. Think that you don't care about self-move assignment, and then one day you find out, oh crap, like I'm doing some algorithm that actually requires that.
It's like environments like that. These are environments that don't use swap very much. If you start writing code that takes advantage of swap being available and fast, or that it sounds like you start writing things up as a result of it. That's how you got to it.
Yeah, well, we got to it in this discussion specifically through basically a buggy implementation of shuffle. So it is possible that you could say, well, I just never really do. But certainly if I were writing code for arbitrary other people to consume, right, that's where I come back to. It's even if I myself can be really, really disciplined and audit all of my code with a fine-tooth comb and convince myself that none of these problems apply to me, I mean that the next person to download the code by running it, wait a minute, this just crashes when I pass it to some other library function. Particularly because these are sort of action at distance problems where, my cat may work perfectly well in my code, and some other guy's shuffle algorithm may work perfectly well with his code because he makes the assumption that something does work. And you combine them, and then everything blows up, and you just can't use them. You just do not play well. And that sucks. So my general philosophy is you should try to make it play well.
Follow-up question on the partition for implementation. Like C99 has this keyword restrict that some people add, but for performance. Now, if you use a swap with a conditional tests whether you are doing self, wouldn't it become the performance copy? Well, not a copy, but I mean it wouldn't be tested.
Are you saying every time you use or every time you use swap, the caller should guard it with if A not equal B? Or are you saying that you should put that inside your swap?
Yes, something probably the purpose, right?
I would rather put that comparison right inside my swap algorithm, right inside my implementation of swap, so that nobody else ever needed to worry about it again, rather than force every caller to do that test. Right? I mean, if the test is going to be there anyway, then I would rather write it once.
Unless I'm sure that it would never happen.
Unless you're sure that would never happen, yeah. Which is basically Howard Hinnan's argument. He says give tender loving care to everything and be careful about everything, which is coming largely from his experience as the C++ maintainer, where he's maintaining the standard library, and really needs it to be as fast as possible for every possible thing. And if there's anywhere where the standard allows you to we don't need to worry about self-move with undefined behavior, therefore I can make this a little bit faster. But in a lot of cases, like, implementing move in terms of swap, like, just swapping these 2 points, it's not really significantly slower. It's undoing it. Unless swapping things is a large part of my workload. Single memory application is going to vastly dwarf any expense of like swapping versus just copying. Yeah.
I started with the question, I think that you know the answer, but I'm curious really, why would the committee not want to add a self-move standard swap? Assuming no backward compatibility. I'm guessing the answer is because branch has a cost that some people care about.
Yeah, why doesn't the swap support self-move? Well, I mean, the really interesting thing there is that I'm pretty sure that it's a defect in the standard right now that std swap doesn't support self-swap, because it doesn't take any R value references. Like it takes 2 L values, and it says, quote, exchanges the values stored in 2 locations. That doesn't say which 2, but under the assumption that it's supposed to swap these 2 values, it should do that if they point to the same location. And I think basically the undefined behavior part of that was introduced in C++ 11 because they read it from being like 3 copies to being 3 copies. It just happens to trigger this undefined behavior. So yeah, I mean, I would love to see swap like do the right thing, self-swap. And I think it doesn't because I think that this gives the library implementer a little bit of leeway to make it more efficient. Anything they can do to make it more efficient. All right. Well, thank you all for coming out. Feel free to stick around and chat, I guess. Dropbox people, take it over.
Yeah, absolutely. Thanks everyone for coming. We have more from here if you are not. Yeah, oh yeah. We'll stick around for a little while.